Thanks everyone for coming, and especially welcome new people at the Bay Area. My talk will be about FMT, or called it FMT. Particularly the cool parts. The title is inspired by JavaScript. The good parts, obviously, all parts of FMT are good, so we'll focus on some technically challenging ones and show which C++ techniques are used there. So a few words about myself. I work at Meta on the Thrift RPC initialization framework. It's kind of similar to Google Protobuf and gRPC together better across. I'm also of FMT library, C++20 is the format, and C++20 is print. Self-proclaimed expert in -0. You can find me on my favorite social network, GitHub, here, and since Twitter/X is kind of dying, we set up for breaking news on that stuff. So the first part of the talk will be about compile time. Compile time, not in the sense how long it takes to compile things, but things that happen in context. And there are three parts to compile time: format string checks, format string compilation, and compile time formatting. Let's start with the simplest one everyone knows about, compile time. With compile time checks. As you might know, format string checks are even available in printf. If you look at the simple example here, simple but invalid example, when you try to take a string and format it as an integer, compiler might give you a nice warning. This one, I remember with Glango GCC, but it's very nicely formatted, very specific. So it says, try to pass cones ***, and we use the %d. You should use %s. This is awesome. The only drawback is that it's an opt-in. You have to pass W format to get this. If you don't get this ready, at least not with the common compilers. Is it really that good? Let's try another example. Let's take size t. See integer. Try to format it to print it as an integer with %d. And now we have a problem. It complains that although size t is an integer, you also with printf have to specify the size of the integer. So what it says that you should really use not d but lb. Anyway, so basically it says that it thinks that size t is long unsigned int. You should format it with %lb.
Why not LU?
Huh?
Why not LU?
I don't know. Ask the compiler. Ask the compiler developers. I think there might be. So can you spot the problem here? Who can spot the problem?
LLU.
LU?
Yes.
Okay. Okay.
Those these are connection dependent.
Yeah, exactly. So size t is actually platform dependent. So if you compile on a different platform, it will give you completely different, exactly opposite. So you use LB here, like your previous compiler told, and now this one compiles that, hey, go back and forth.
Well, there is %z for that.
Yes, exactly. But it doesn't tell us. Where is it? So these compile time checks are limited. They don't understand type depths. They don't understand only do basics. Wow. So all of that is QI, and Q, which stands for quality, is very low. Y stands for open to. So how does it work in FMT? The compile time checks. They are enabled by default in C++20. This is an illustration of the same example as before. We take a string, try to print it as an integer, and if you use C++20, it will give you a compile time error. The error is not ideal because we have limited mechanisms to report error messages in the compiler, so it uses some trickery, like a non-consecutive function here called CppBayArea, but it gives you enough context and information. So basically, it gives you the location of the error line and also the message in valid formats. Not to go and debug them. And you can even write your own functions that do the same compile time checks. So to do this, all you need is this format string type, which takes as template arguments your format arguments, and then you can have a function like this log function that take a format string and some arguments and forwards everything to print. And it gives you the same compile time check. So all the logic is within the format string. Don't have to write any other than say this is a format. So how it works under the hood? So it relies on kind of three pieces: C++20 const eval, which if you reference specify that the function is an immediate function, blah blah blah. So basically, it means that this function is evaluated only at compile time. Second important component, and is very subtle, the most tricky one, I think, is using type identity to suppress complex argument reduction. And I'll show later how to combine all these. And finally, the easiest is converting constructors, convert from strings into these formats. So let's implement ourselves this format string. But because it's difficult to write the parser for all the format strings, we'll use a simplified syntax, just recognize curly brackets. A pair of curly brackets. It's very rudimentary format string checker. So basically, we have, and it only accepts one argument, one formatting argument. Most useless formatting. I like to string. So as I said, we first use const eval, our first component. So the constructor of basic string is const eval. It's evaluated at compile time. The second thing that you might notice is an implicit constructor. So if you pass a string into a function that takes basic format string, it will be implicitly converted, and at compile time, it will be invoked and run this code here. So this is kind of how we run the code with checking at compile time. And this is, here we have a little bit of parsing code. It's a silly parsing code. It looks kind of assumes that S is convertible to ***, so it may be a literal memory of characters for a pointer, star pointer. So we check if there is an opening, curly bracket, closing curly bracket, and everything else we skip. But if we had found this pair of curly brackets, we create a formatter of T, we create format parse context, and we parse we forward parsing to this kind of infrastructure using FMT. We won't go into too much detail, but basically this illustrates the kind of high-level mechanism with which compile path checks work. So this is I mentioned the third component is type identity. So why do we need type identity? It's to prevent type deduction. If we go back to this, or if we go forward here, we have our basic format string. We have our ls with type identity. We have a function that takes a format string. So if we didn't use type identity, you would try to deduce the type of this thing here, deduce the template parameter from this thing, and it will fail. So we need to disable deduction in the format string. Then our implicit constructor kicks in, and we can get our compile time, our code for checking product component. Hopefully it makes sense. And then we can actually try this, and all the code that I showed on the previous slide actually works and gives us some rudimentary techniques. So look, we implemented compile time checking in one slide.
How does type identity work? How does that type identity work?
So type identity, I don't know how it works.
Okay.
I know what it
Okay, so
the simple answer. It disables type deduction. Complete. So the whole purpose is that there's no deduction here, so it's like a concrete type. So T here is deduced not from first argument, but from here. Then when it's deduced from there, it is plugged into format string, and it's a concrete type, and then implicit constructor can kick in. It's the trickiest part of the whole thing. It took a while to kind of figure out. I think Tim Song because I had no idea. So it also works for user-defined types. So I showed you earlier that we create a formatter and call parse there, parse something, format parse context, which basically give you the current position parse format string. So it works with user-defined types. All you need to do is to make this parse function a const expert, implement your parsing. For example, here we have a struct called answer with an integer inside. We want to format it either it's hexadecimal or default with decimal. So we parse an X specifier here, and at formatting type we check the format specifier and call. So yeah. And if we put it all together, we have full compile time checks for the top level, the structure of the format string with braces, and internally for format specifiers. This is how it's done for you in one text. Yeah, and we can test it again with our simple rudimentary given format string. It works. Up here it is not rudimentary, it's our actual print, but we even worked with the previous the format string from previous. So now let's move to format string compilation. So what like compilation? It means that we take a format string and convert it into something so that it doesn't have to be parsed again at runtime. Let me show you an example. So there is some rudimentary format string compilation in sprintf. it's not a very serious example, but kind of illustrates the point. So we have printf and we want to print hello world. Actually, if you look at the compiled code for GCC, I think printf goes away. There is no parsing of format string. It figures out, oh, this is like a literal string. It doesn't have any dissent inside. So let's just call putas. And putas doesn't care about format strings. It just prints everything to self. This is great. Feature. I would expect it be able to do similar things, like understand %d maybe and do something clever here. But unfortunately, that putas trick is the only thing that compilers know about. If you try even something very simple like sprintf convert 42 to an integer, it will still call sprintf and do parsing at runtime. So kind of upgrade. In FMT, you have a choice. By default, it does only compile time checks at compile time. It does only format string checks at compile time, but you can opt into format string compilation. The way you do it, there are two ways. There is a fancy way through literals, the CF literal, user-defined literal, which stands for compiled format. And there is a old school way through macros for older. So and if you add this CF user-defined literal to format string and don't change anything else, it magically removes any processing of the format string at runtime. So what it compiles to is just storing 4 and 2 ASCII characters at the address. It basically compiles into 3 instructions and return. Magic. So how does this work? So again, we rely partly on context for parse functions. In the data specialization, we saw them previously where they were used for checks, but we can also use them to construct this formatter object at compile time, store them, and reuse at runtime. For built-in types, it's even more efficient. We don't do any of that. It's efficient. We also need C++20 class types and non-type parameters feature, very and TTP. Then we need the C++17 construct with if, and something from C++11 user-defined literals. That's what with the second features. So these 4 components. Yes.
So on the previous one, you had to use the user-defined literal to get it to be a compile time literal. If you didn't do that, would it still work? It just wouldn't be compile time? Like if you drop the C_CF.
If I drop _CF, it would create a call to reformat2, which would parse the string at runtime.
But it would still compile.
It will still compile.
You just might not know it.
You get the runtime cost every time you call it.
Yeah.
So the difference, the runtime processing of format string versus compile time processing.
But if I naively did it, how would I know?
You have CF, so naively did what?
If I naively forgot to put the CF in there,
You don't need to put CF. If you don't put CF, it still works. Everything works. It might be slower,
right?
A little bit, but it works. It will
benchmark.
probably still be faster than sprintf. So there is no tragedy there. But if you want to squeeze even more performance, you just plug in CF, leave everything else unchanged, and hopefully you'll get better.
Right. And you had to make it a literal there because you couldn't have optimized it without a literal?
Yeah, that's a good question. In principle, it's possible to do something even without a literal by default. But there are some trade-offs. I'll return to it later. More questions? Find your way.
It's really good. It's really good.
The way of slides. So how it works, we covered that. Yeah, let's implement this quickly on the slides. Non-type template parameters. So what are these? Basically, it's a way to pass string in the context of FMT is a way to pass strings as template parameters. So first we need some infrastructure. We need a fixed string because C++ doesn't give us. So we need a fixed string, which is basically an array of characters, size n. And here we just plug in this fixed string as a template parameter, and it's great. So we could use format, angle brackets, this string, what I do. So this is a potential other API, which FMT doesn't do for reasons, but it's possible. And the reasons, actually, I should say, I thought I had slide. The reasons why we don't do it, because it would interfere with the argument position. So it's not ideal API. So when do you use message? Instead, what we do, we use user-defined literals. So in addition to that fixed string, we also have another struct called compiled format, which represented a compiled format string. We have this compiled format returned from our UDL. And it's a fancy UDL. UDLs were introduced in C++11, but this one is constant because it uses this MTTP. And it's kind of tricky. But basically, what happens is if you write your string with this UDL, the compiler will translate this into something like on the right side of the comment, called to this operator. It magically puts your string in the template parameters. With the way kind of take your thing and put it into template parameters. It's very nice. It's difficult to understand, but perfect C++ feature. Difficult to understand, but sometimes useful. So yeah, so basically that's all there is to that CF thing. It will convert into this thing, and the result will be an object of type compiled format, which is simply our string format string. So it's a very roundabout way to get our string into the template land. Okay, so we have putting all together, we have this compiled format, we have UDL, now we have actual desirable API format that takes compiled format. In previous, so the default API takes, instead of compiled format, if you remember, it takes format string. This is a different overload. That's basically for the API part, but we also need to implement the compilation. Implement is in general is quite tricky. Basic idea, we use context for if to do some logic to translate the patterns into simpler ones. For example, in this case, we can recognize the default format, just a pair of curlies, and we convert it into two-string code instead of following the whole format. So this is like the simplest way to compile. We just optimize one case. In practice, it's more complicated. So in practice, we have a function to compile the format string, the detail compile. And if we look at the type, this is a with pseudocodish. Basically, we get a nested kind of a template struct with some nesting that represent the format string to compile for. So here we have a little bit of literal text. The answer is followed by a space, which is represented by text here. This literal text followed by, so this is concatenated with the field, which is a pair of curly braces referring to an integer field, followed by a single code unit, the dot at the end. So it is compiled into this object. And this object this type has a format function that knows how to output itself to the output iterator. And this is kind of one simple example of what is the text here. Text is that it represents a piece of literal text. So it's just a string view which knows how to copy itself into the output iterator. So it's one of the simplest. And then we had field, which represents a single reference to a single argument from any argument, which extracts this argument from the list of arguments that is passed to the format member function and writes it to the output iterator formatted. And we have a bunch of these types for different cases. Text here, field, the third one, the code unit, concatenation, where it puts first part, then it puts second part, and so on. And yes.
Can users extend those optimizations?
They cannot extend it, but when they write their own formatters, their formatters are supported. So one of these primitives is the user formatter. And so maybe within this formatter, you could do some tricks. Yeah, the more complicated is, the less benefit there is to this calculation. This kind of a short concept. Okay, where were we? So this is text field, a few examples. And if you put it all together, how it works, so if we have a call to format to, which takes a buffer, format string, and integer, it is roughly equivalent to calling FMT detail compile, which creates that compile object that I showed on previous slides, and then calling the format function that outputs this object. So, so this conversion happens at compile time, and the actual output happens at runtime. There is no processing of format string at runtime. And we can look at benchmark, how much it helps. So there's FMT with format string compilation, without the default printf, two chars, two string, string. And so two chars and FMT compile. So the two benchmarks. The sequential, which kind of goes in the order of increasing digit count, bundles inputs with the same digits together, and random is just completely random. And so on sequential, we have roughly the same performance with FMT compilation with two chars, which is pretty great because FMT is much higher level API, easier to use. And with the random, FMT is even faster But there is no reason for one to be faster than another in this choice of algorithms. So in principle, these should be the same. Runtime is slower, but it's kind of comparable with what you would write by hand with like a this is the same. You can illustrate it. You see a string like super terrible price. This string is actually not too bad, and I think they recently improved in lib C++. So it might be even better. Yeah, this is a breakdown of benchmark by digit count, and this is a choice of algorithm. So neither two chars nor FMT with compilation dominate each other in terms of performance. So blue is FMT is faster and smaller when the number of digits is smaller. Two chars is slightly faster by the number of digits. So one indication, why not return to the question, why not use format strings compilation all the time? It's like so good, right? So the answer was in this file. There are people from Apple, I'm sorry, I apologize. for stealing this mean material keynotes. So basically, the problem is trade-offs. The trade-off between performance and code size. So if you compile, you get like potentially a lot of code load. Really complicated cases. If you do it runtime, you just use the same implementation, but not somewhat runtime, but very compact call size. So it needs to call the format of the print. There's a trade-off there. This is why it's opt-in rather than.
What's the code size for the impact? Is it because, okay, so with the runtime, I just have the format string literal. Like I'd have to have the literal somewhere in the code to say how to format things. Is it because, oh, this results in a bunch of code that is generated?
Yeah. Yeah, it's because this thing, it generates this templated stuff that knows how to format each individual part.
Right.
So for simple cases, it might be okay. Like I showed, it can give you 3 instructions if you convert an integer into a string. But if you have like complex thing, then you get this templated thing, these format functions. Each of them has a bunch of code to format just itself.
Right. So and even in this case, this compiled format, .42, and if it can resolve, it's like, hey, it's a literal that is, the answer is 42 dot.
Yeah.
If you use that same compiled, like with a bunch of different numbers, they could be a bunch of different literals in your code, as opposed to one string format.
Right, yeah. So there are probably some optimization opportunities for binary size there as well, because you can maybe raise the size or something. But yeah, generally, this is very kind of, and also this format, individual for. The last part from compile time. Compile time formatting. So this is the simplest one. For those who are not asleep yet. For example, let's try to implement a conversion from integer to a string that works in compile time. What we need, we can just use const where we take our format string compilation thing, where the previous part, and just do everything at compile time. Store the result in the array, and it works, and it just gives you the 3 bytes. So nothing runs. Everything is static data in the result. So there is no magic here. Just const for all the things. You go through the library and put const everywhere. But there is one problem here. If you have static data, then it's kind of problematic. because you cannot, until C++23, I think, you cannot have this tables, static unstructured data in your functions. You either have to remove static, do some other tricks, doing static generate suboptimal code. Yeah. That's life finds a way. So there are workarounds for this. You can have a separate non-context for logic. You can use that if context for, or you can store data outside in a class. Or you can use string literals. This is my favorite
That's
thing.
beautiful. Oh my God.
Yes. Well, this is the only use case for you string literals that I found.
What?
So basically, it's an array of 32-bit integers encoded as a Unicode string literal. So in C++23, you want to do the right thing. So the second part of this talk is about type arranger. It will be smaller, so bear with me. So we use type arranger in FMT whenever there is a danger of template load. We see like templates, especially with ... it's like means like ... means template one. So there are two main places. Actually, three main places. One not listed here is trivial type arranger for strings. We convert std string, other strings into string view. Nobody calls it type arranger, but it's kind of geometric type arranger. But the important ones are formatting arguments where we have these args involved. It's very dangerous. In another case, it's output iterator. So all of these, if uncontrolled, can create a lot of template instantiations. This was a real problem because in Poly, so we still have Poly format. We actually didn't do any type arranger, and we had some problems with. So is it actually a problem was solving? For example, let's take this post-string string case. How much code do you think it generates?
Way too much.
This is like hello world in higher streams. And to like pick the tiniest font, and you won't see here, but there are like dozens of calls and some functions like manipulated. I don't know what's going on. So naive implementation, what would it do? It would do everything in the format function. You don't care, just do the parsing and formatting. Then the problem is that format int, it generates a ton of code. Format double generates the same amount of code. Terrible. Then for strings, it's even worse for string literals, because every string, it will create instantiation for every distinct string literal size. For example, here you have 2 characters plus terminating null, so it will associate for one-star array, reference to array size 3. Not great. So what we do, we use type arranger. So the format is actually forced in line, and what it calls inside V format is a type erased representation of arguments called format args. Then all of these compile like in very short code sequences that call V format. This is actually what it compiles. So this is equivalent of that live stream example where we had like 2 columns of very tiny things. Here is a dozen of instructions, and only a single call to V format. That one has magic code with some. So they're cheating, but they are the same for they're shared between all the calls to V format. How it works, yeah. So format args is just a collection of a span of objects of type format arg, and format arg is essentially a variant of some built-in types and a handle for user-defined type. And also we have things called format arg store, which is an array because span doesn't own anything. We need some owning thing. So store owns thing, and args is a view into this store. Make format args creates this store. That's it. So basically, in one slide, we implemented type region, except for like your details. So it's not the actual variance to variant. It's like variant. It's more efficiently represented. Format args are not actually span. It's something different, but kind of conceptually is how it works. We kind of calculate all these things, and at runtime, kind of dispatches into the actual types and does this magic. So I was skeptical. Cat thinks that it's familiar, and yes, it looks very familiar. People who use printf because it's basically the same thing with printf and eprintf had this kind of representation of arguments of EA lists, kind of similar. But FMT's version is more efficient, and it also works with user-defined types, and it's type safe. Question?
Yeah, how does the user-defined types can register? Like, is that like some tricks?
User-defined types. So basically, there's a handle that kind of we use lambdas, and this handle kind of creates as a pointer to this lambda. And the lambda is different for every user-defined type, and this lambda knows how to format the object. It's kind of similar to any where you have like other cases where we have type erasure. I don't have time to go into in detail, but basically it's like a function pointer that knows how to format and pointer to object, and function knows how to format the object. And another part where we can use type erasure is iterators. So we convert iterators into buffers. So there is a base class buffer, which is a pointer to data size, capacity, and one virtual function for growing. And there are different types of buffers. There is like a general case iterator buffer. So there is one for optimized for pointers, optimized for other non-pointer contiguous iterators, and the general slowest case for arbitrary non-contiguous iterators. So it does additional buffering to split it up and kind of avoid code bloat. And also there is a counting buffer, which allows writing into itself, but it discards all the options. It doesn't grow, that's itself, and writes from the beginning. Iterated type erasure, it's also pretty simple. So we take an output iterator, convert it into one of those buffers, showed it in the diagram previously. We do the formatting, but now not into the iterator, but in the buffer. So here we don't have any template load because buffer is just the base class. It's a reference to the base buffer. And finally, we convert buffer back into the iterator. Does it matter in practice? Yes, we did this in fully logging library. We got some nice reduction for code binary size. Logging, you don't need you don't want like too much load because logging is using it throughout the code in many places. Samples, so you don't care about things, all code rather than. It's like the final part of my presentation is about floating point formatting. Best saved at the end. Yeah, so let's start from the sad things and work after next week. So formatting defaults are a problem in C++, C, other languages, APIs. So we look at this example, like we add 0.1, 0.2, we compare it to 0.3, should be same as the other thing. It will give you very interesting output 0.3 equal 0.3 is false. So yeah, why does it happen? So the problem is not specific to C++, but problem is partly, well, in this particular case, the problem is hidden. So we don't see this rounding issues, the actual representation issue. So decimal fraction cannot always be represented in binary precisely. So you have this like 0.1, blah, 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 with 0.3, many zeros and 4 at the end. And when you add them, you get different rounding behaviors, and that kind of explains this this difference. But the problem here is not that they're different, but why is displayed the same but says false? So the display actually defaults are wrong. It should actually give you the full information. There's lots of information. The main point. And the desired properties of floating point formatting have been known for a long time. So this is paper from 90, but it actually originates from 70s. Still, and why they came up with properties of the adding floating point formatting algorithms, and the desired properties we don't want information loss. We want modest output, correct rounding. They also have the false property, and left to right generation of digits. It doesn't matter anymore with modern computers. It only matters if you write to like a tape or something, digit by digit. And I would denote this set of properties 1 to 3 with like unicorn or ideal algorithm. Any algorithm. So let's look into all these properties details. So no information loss. So basically, we want round trip. You output, you parse it back, and get the same result. I love this nice thing. But amazingly, most libraries function like this property, unless you explicitly say I want like big precision and specify exactly what precision should be there. For example, sys.io, C++ string to string until C++ 93. You are welcome. Fix the string. Python's SCR format until version 3. So all of them lack this round trip property, like basic property. Okay. Here's an illustration. We have some double, we printf, we read it back, and it's not the same. There's this magic 6 digits of precision taken from. So if we use our unicorn algorithm on the other hand, we would get perfect result. What we read back is the same that we looked at. So the second property. What was the second test? Right. Kind of what about yes. Actually, this is more, it's less about shortest output, but if you want round trip, you could specify big enough precision. What is the big enough precision for floating point? So it has been known again from 60s, this in and out conversions paper by David Patua. And if we plug in the numbers for IEEE double, then we get 17 digits. You can actually get the round trip property if you plug in 17 with the correct specifier. But the problem is that it conflicts with our second property. We get round trip, but we now don't get the shortest output, so we lose the second property. So, for example, here, if we try to print 0.1, it will give you 0.1001, while in fact, it is uniquely, the same number is uniquely identified by just 0.1. So there is a lot of garbage digits here. And garbage is actually a scientific term used in the paper by Steele and White. And the third one is correct rounding. This is kind of obvious. Correct is better than incorrect. So we usually correct, well, different rounding modes usually is near to nearest, nice to even. IEEE 754 default, but even that is sometimes, well, at least in the past, even rounding was broken in Microsoft underline. Maybe it fixed all of that, but it was broken for a long time. So how do people approach this? So there are lots of floating point formatting algorithms. There's actually a research area these, and they all dragon themed.
Mhm.
And dragon comes not from like mythical dragon, but this dragon curve. Again, it comes from the paper. Right? So they have, many of them have this dragon name. So some of the popular algorithms, state of the art, and not state of the art, the last one. One of the latest is Dragon talks by Jim Key, who contributed to the FMT. It's amazing work, and now it's the details of FMT. It's based on another algorithm, Schubach, also recent, 2020. It's like, people still coming up with algorithms. Then there was a pretty popular one at some point called Ryu, I think it's used in Microsoft STL. And then there is a whole family of algorithms called Risu, used most famously in Google double conversion library. And for a long time, FMT has been using this until we switched to Dragonbox. And for exotic floating point, we use Dragon, which is like general case. It uses multi-precision arithmetic.
What is exotic floating point? What is exotic floating point?
Exotic is like 128. It's,
Okay.
well, it's not very exotic, but
Long
you don't
doubles.
require very large tables to do any of these. Okay, so what does printf do? So it actually depends on the implementation. The problem is the range is very big. So in general, as I said, it requires multi-precision arithmetic. Does it actually use multi-precision arithmetic? Let's check. We can profile actually call printf with some double and look what's inside, and actually it does. So this is we caught it in action. It uses multi-precision in glibc. These parts of it. I particularly like this function called hack digit. Something really fancy going on, and we have hack in here function. Yeah, so it looks like it uses something like Dragon maybe. So in FMT, as I said, we have all this nice property. It's a unicorn algorithm. The default is the shortest decimal representation with round trip guarantees and correct rounding. So there's rich formatting, mini language, supports iterators, and relocate buffer. So this is different from two charts. So you can actually don't need to know the size of your buffer. You can do it in one go. And avoid copying. In general, copying seems like a cheap operation compared to floating point formatting, but because this algorithm has become so fast, it actually matters now. You can avoid dynamic memory allocation, control the cow. So here's illustration round trip. So same example as before, you get nice properties, everything is preserved when you parse it back. Locale independent by default, unless you specify your capital L, which will ignore global locale, it will ignore any locale. If you specify it, it will use the decimal point to be replaced with whatever decimal comma is. Zero allocations, so you can completely avoid allocations. For example, if you for the default, you actually know what's the largest possible size. You can allocate the buffer big enough, and right there. You can use FMT memory buffer, reach points allocation by default, but can grow bigger if your output size is bigger than expected. Yeah, as I said, it's all benefit compared to because there's so it will allocate the correct size and write into it instead of you providing a good buffer, writing there, and then kind of copying it. And this is another benchmark now for floating point. Bunch of algorithm string printf, double conversion, view FMT. A little bit outdated, fortunately. So I think Ryu has become, not Ryu, Dragonbox has become faster. So now where integration is actually the slow part. So we can go back and optimize that. So it will change in the nearest future. But basically, you can see this is logarithmic scale. So back at the top, which is bad, is like O string, printf. So there with cluster of low things, which is your standard library. Except for two chars, new things, two chars. With two chars is not here, but they could use Ryu or one of the algorithm. So among faster ones, FMT, which uses Dragonbox, but a little bit suboptimally, and Ryu, so they are similar situation as with integer. So FMT is faster on shorter outputs, and Ryu faster on longer benchmark. So I think the property of Dragonbox is actually better than Ryu. So because unless you write completely random, have completely set of random doubles, you don't need to always output up to 17 pages of precisions. From this perspective, Dragonbox has nicer properties. And finally, we go out to hacking CPP, who put together this nice cheat sheet for FMT, which kind of gives you all the format specifiers in one little picture. Actually, have lots of these features. Check it out. Oh, my manager told me that we are hiring to. So if you like to become a meta programmer, go to meta careers.
Does that mean a lot of templates involved?
Yes, all of that you should know. This will be questions. Any questions?
How does your memory buffer work?
Memory buffer. It's like it looks like small string optimization. So there is a new line.
But it doesn't know the size until you try to actually format.
Yeah, it has some predefined size.
But then does it allocate then, or what?
Initially, it doesn't allocate. So
Yeah.
if you write it and it fits into the single line buffer, it won't allocate. But if it's bigger, then it will allocate.
And one more question then. When you're compiling a format string, is there a limit? Because each format item in the format string becomes a template parameter.
There is no limit. If the buffer is not big enough, there is a grow function. It will reallocate.
No. I mean, like in terms of the compiler expansion of the compile time templates.
Oh,
parameters.
templates. Yeah. Oh, there's definitely limits.
Yeah.
I haven't hit these limits because I only use this for
Small. Yeah. Okay.
So this it mostly benefits simple cases. More complex formatting is less.
Thanks.
Any other questions?
Two quick things. One, the performance figures for like O-string stream and friends, that was the GNU-C library, or libc++. Which did you benchmark?
Yeah, I don't remember this particular. I think it's probably glibc. and libstd C++, more likely, because it's been done a while ago.
Okay.
Probably another version, so.
And the other thing, do you happen to know if the compiler or linker or both will deduplicate compile time format strings if they happen to be identical?
Format strings. So they might deduplicate some of them because
Template instantiations, right? They get link ones.
Yeah, it really depends on how you implemented it. So that's
with that. If you look at this compiled thing, think about. So this compiled object, and it do duplicate them. Yeah, I don't think it will duplicate because data is actually stored inside. Well, it might look at this and do some magic, but I doubt it. Probably not.
The data is part of like the data structure, becomes some code, like the string literals are part of the data structure. What you mean?
Yeah. Well, this thing is known at compile time. It's an object with some static, well, not static, with some data inside. It is known at compile time. And in principle, compiler could duplicate it, but I don't think it would do it.
do you know, like, do all of them have different types, the objects? Usually it'll deduplicate on type bounds.
So common cases is just you have something simple like curly's inside, and then there's a lot of sharing involved, I guess. But still, I'm not sure if it will go like a duplicate. So in case of field, it actually has no data. So if it's just field, so everything is templates. So this one will be duplicated if you have just curlies. If you have text and curlies, it's a different story.
How do you print negative
It gives you correct these minuses and everything.
Really? Okay.
There was a question.
Oh, so this is a bad question without context. So the question is like, why should someone use FMTLib? And the context is recently the project I worked on, we switched to C++23. And the only reason we did that is to get rid of FMTLib and switch to using std format.
I'm all in favor of that. So the switch format is like
What's
the same thing.
Oh, really?
Yeah, I don't need to maintain it. It's even better.
Going into the future, will there be any work on FMTLib? Or
Yeah, work continues. So FMT is a superset of the stuff. So some library doesn't have some of that doesn't have format string compilation.
So then if FMTLib is just better, then why shouldn't you use FMTLib?
I mean, it's better if it satisfies your requirements, then use it because you have fewer dependencies, and you know in C++ dependencies are very hard.
It was actually a regression because now there's like no print function, no ranges formatting. So it's like,
You said C++23.
yeah, but it's not fully implemented in GCC.
Yeah.
So it's,
Complain to your vendor, not to me.
Actually, so now that like have std format as a competitor, like to what extent do you actually like think about interoperability and what is inside the standard?
Yeah, we try to be consistent and historically fixed a number of discrepancies. When floating point, there is one currently small discrepancy in how you interpret the shortest, but mostly it should be like drop-in replacement.
So a follow-up question: Do you also get like to still like basically collaborate with implementers on format?
Yeah, so occasionally, so especially in the early days, we collaborated a lot. Overview and discuss the various features, it even, there was an input from implementers to the standard, which ended up in FMT. So it's like a bit of bi-directional process.
So you wrote the original FMT lib?
Yeah.
And then you made it into the standard. How was that process for you?
It was a pain. Well,
But you did it,
it
right?
took 3 years. Yeah, it's a very comprehensive process, as it turned out. I probably just submit a paper, and next day it's approved. But it helped a lot. So the input from the committee greatly influenced the design of later versions of MT, and with all the iterated stuff, the format to came from the for better or for worse.
So how should projects currently using like printf style formatting migrate to either like FMT or STID format? Is there a client ID check maybe that
Yes,
rewrites it?
there is one ID check.
Can you tell us about it? Is it reliable?
I don't know anything about it other than it exists.
That it exists?
It
Okay.
has its limitation. Obviously, things have to be known at somehow. Not sure how robust it is, but I think it's a good starting point. I don't recruit and tweak software. I think the information of this slide should have been.
So was the plan always to make something that could go into the standard? Or did you like build it and then people were like, you know, we could just have stood print. And you're like, oh, I guess
No, the plan was to have something in a week or two for my small compiler project to record diagnostics.
Got
That
it.
was the original plan.
So I'm currently maintain a LLVM backend for the 6502, and I'd love to run FMT lib on it, but it's the most bare metal of most bare metal platforms. So like, how separable are things like allocation and stuff like that in FMT? Like, you take parts of the functionality and leave others behind.
Allocations probably not separate. They're kind of integral to the standard library. So we don't allocate explicitly, but the use string format, FMT format returns string that may allocate. So if you solve that problem for standard library, kind of.
So it has a strong dependency on the C++ standard library to work.
There is a pretty strong dependency. Some definition is strong, but some other components can be disabled. For example, locales can be completely disabled through the processor. Even floating point can be disabled because people use it for embedded, where you don't want all these fancy algorithms that I told about. They are great, but they generate a ton of cable.
I kind of did run this on a bare metal program before. Like especially with the compile time format, like the format string compilation, most of the things it like disappears.
Yeah.
It's like as long as you do the format, like compilation should be fine.
Yeah, that's actually a good point. If you use the format string compilation, then and maybe a link time optimization, everything goes away. All the library goes away, so you don't need to do anything. But you are restricted to API and also what you use, what formats you use. They don't pull in.
All right, let's give another hand to Victor